Ever wondered how artificial intelligence, once a figment of science fiction, now powers everything from voice assistants to autonomous vehicles? The journey of AI is a tale of relentless innovation, where theoretical breakthroughs collide with real-world challenges. Today, we're diving deep into the technical heart of modern AI, exploring the architectures, algorithms, and principles that make today's systems possible. Buckle up, because this is more than just a walkthrough. It's a crash course in the mechanics of machine intelligence. Let's start at the beginning. The foundation of modern AI lies in neural networks, computational models inspired by the human brain. But here's the catch. Early networks were limited by their simplicity. They relied on feed-forward architectures with just a few layers, struggling with complex patterns. Then came the backpropagation algorithm, a game changer. By calculating gradients through the network using the chain rule of calculus, it enabled models to adjust weights iteratively, learning from errors. But even this had its limits. Training deep networks often led to vanishing gradients, a phenomenon where error signals diminish as they propagate backward, stalling learning. The solution? Rectified linear units, ReLUs, which introduced nonlinearity without the saturation of sigmoid functions. Suddenly, networks could scale deeper, unlocking new possibilities. This breakthrough wasn't just theoretical, it laid the groundwork for the deep learning revolution. But how did researchers tackle the next hurdle, data efficiency? Enter the transformer, a model architecture that redefined natural language processing. Unlike recurrent neural networks, RNNs, which process text sequentially, transformers use self-attention mechanisms to weigh the significance of each word in a sentence. Here's the technical nitty-gritty. For every word, the model computes query, key, and value vectors. The attention score is the dot product of the query and key, scaled by the square root of the key's dimension. This score determines how much focus the model places on each value. The result? A dynamic, context-aware representation of the input. But why does this matter? Transformers eliminate the need for sequential processing, allowing parallel computation. This scalability enabled models like BERT and GPT to handle vast datasets, achieving state-of-the-art performance in tasks from translation to text generation. While transformers dominate NLP, the broader AI landscape faces a different challenge: generalization. How do we build systems that adapt beyond their training data? Enter meta-learning, training models to learn how to learn. One approach, model-agnostic meta-learning, MAML, optimizes a model's parameters to quickly adapt to new tasks with minimal data. The idea is simple yet profound. The model learns a set of initial parameters that, when fine-tuned on a new task, converge rapidly. This is achieved through a two-step process. First, the model is trained on a distribution of tasks, updating its weights to minimize loss. Then, it's tested on a new task, with the goal of achieving low loss after a single gradient step. The result? Systems that generalize like humans, requiring just a few examples to grasp new concepts. These advancements are impressive, but they're only part of the story. What about the ethical and practical constraints shaping AI today? Despite their power, today's AI systems are statistical pattern recognizers. They lack true understanding, relying on correlations in data rather than causal reasoning. This leads to brittleness. Models can fail catastrophically when faced with out-of-distribution inputs. Researchers are tackling this with causal AI, which incorporates domain knowledge to model relationships between variables. Techniques like counterfactual reasoning and graph neural networks aim to embed structure into models, enabling them to reason about cause and effect. But the road ahead is fraught with challenges. Computational costs soar with larger models, and ethical concerns around bias and transparency demand urgent attention. The future of AI isn't just about scaling. It's about building systems that are robust, interpretable, and aligned with human values. So where do we go from here? The next frontier lies in hybrid architectures that combine the strengths of symbolic reasoning with neural networks, and quantum machine learning, which leverages quantum mechanics to solve problems intractable for classical systems. But for now, the lesson is clear: AI isn't magic. It's math, engineering, and a whole lot of hard work. If you're as fascinated by these ideas as I am, hit subscribe. Let's keep pushing the boundaries of what's possible, because the future of intelligence is still being written, and it's being written in code. Thanks for watching. If you want to dive deeper into any of these topics, check the description for links to papers, courses, and tools. Until next time, keep questioning, keep learning, and remember, the most powerful AI is the one you build with your own mind.